Okay, let's have a class. We will continue to talk for the exam 3. We will go over the organic chemistry today. And basically, we'll go over the energy calculation, all these basic knowledge. Okay. I'm using a different way to present. All these slides we could be compiled together, and we'll explain to you the different material. So let's talk about this one. We start to talk about this section. We talk about the electron transfer. And the electron transfer, we talk about that in your biochemistry class or your chemistry class. You know about that. Like, let's say oxygen. Do you remember these things? If you good at chemistry, this is 1s, 2s, 2p, then go up, down the electron in the sublayer orbital. Is that right? Up, then go down, then follow Hund's rules and Pauli exclusion policy. And blah, blah, there's a lot of, in the chemistry, you talk about that. And we're not going to go over these, but we will give you an overview concept of the using electron to explain the biochemistry reaction. So what this means, electron transfer, they always have a donor and acceptor. If the electron transfer donor is an organic chemical, and the electron acceptor is also an organic chemical, this process we call fermentation. And if the electron donor is organic chemical, and the electron acceptor is an inorganic chemical, we call this is respiration. Now it depends on the different type of the inorganic acceptor. We could separate respiration into the two different categories. If the inorganic acceptor is oxygen, we know this is aerobic respiration. If the electron acceptor is an inorganic chemical other than oxygen, let's say it could be sulfide, could be nitrogen sometimes could be carbon dioxide even. Okay, this is, we call it an anaerobic respiration. So this is what we talk now. We want to mention something here very briefly, not going to go detail. What I'm writing here is what we talk about in this slide. Aerobic respiration, anaerobic respiration, that's what's explained, could be using this table to explain about that. Now you always remember, in the microbiology standpoint, the best way to describe fermentation is always talk about electron transfer from donor organic chemical to acceptor is also organic chemical. Okay, so let's talk briefly about fermentation. What is fermentation? What is fermentation? We basically have two types of the fermentation. Number one, everybody knows is pyruvic acids. Pyruvic acids, pyruvate, become lactic acid. This process is called homofermentation. They could have a second thing happen, is pyruvate become aldehyde. If you know aldehyde is like this, okay, I'm just skip all these chemicals. They finally become alcohol. Or we call ethanol. This is called hetero fermentation. because they generate the final products with something other than acids, other than lactic acid. Now we know that if this one continue to do, will generate acidic acid, that is vinegar. So the vinegar usually is a secondary or tertiary fermentation. We will have one class talk about the vinegar making the vinegar, okay? So that's the fermentation. We do very simple tell you. Fermentation, you always remember, they have a very limited energy generated. Only 2 ATPs generated. And these 2 ATPs going through substrate level phosphorylation. And we will talk, there is another way which is called oxidative phosphorylation. Oxidative phosphorylation. We will talk about that. Okay? Now, where this pyruvate comes from? This comes from glycolysis. And then we will talk about the glycolysis real quick. So, that is a picture he's showing you. Always keep in mind, bacteria can survive in the anaerobic environments. They must be coupled with glycolysis. The glucose going through glycolysis generates pyruvate. And they will go either hetero or homo fermentation. Now, why they can do that? Why even only 2 ATPs the bacteria can survive? The reason is those processes can recycle electron, which means they coupled with NADH oxidized between NAD plus. Nicotinic adenine dinucleotides and become nicotinic dinucleotides dinucleotides proton become nicotinic adenine dinucleotides. This is a well could always carry another electron with it. So always remember, that's a very good question. Always asking people, why fermentation only 2 ATPs? They can survive because the electron is recycled. Okay, so that's a very easy example to tell you the fermentation. This is the slides. Explain the products for the fermentation. It is very interesting. There is several things we could talk. First of all, probiotic bacteria. This will generate CH3, CH2. This is propionic gases. What is this comes from? Where you show this one? Swiss cheese. See these holes? Swiss cheese. That's carbon dioxide. And tastes very acid. That's Swiss cheese. And this is a short chain fatty acids, propionic gases. Lactic acid, you know that. In a yogurt, in the soy sauce, in the cheddar cheese, there's a lactic acid. Wine and beer, they're going through secondary fermentation, they're going through hetero fermentation, generate alcohol. And of course, there's a bubbling, which is carbon dioxide generated. We'll talk about the beer brewing sometime. We'll see whether we have time. Okay, we want to try to do that. So some of the girls using nail polish remover. You can buy one bottle from Sephora, some places. That's sometimes expensive, not really cheaper. It is acetone. Now where they come from? Very special, comes from Clostridium. And at this moment, this Clostridium is not difficile, is not perfringens, not tetany. It's a beneficial bacteria. Because in general, the acetone could remove the nail polish chemicals. So always remember, Clostridium in certain conditions could generate a beneficial material. The last one, vinegar, E. coli, and acetobacter going through secondary fermentation. So we have acetic acid generated. Most of the time in the vinegar, the acetic acid is 5%. This E. coli is not generic E. coli, not E. coli over 57H7, it's E. coli 9037. The very special E. coli. In 1937, people first find this one could be used to ferment it with vinegar. Okay, so this picture, which is giving an overview, during the fermentation, we could generate a lot of very good products. Certainly, it's beneficial. So that's very simple. Overall, we talk about fermentation. Now, what we're going to talk about today is aerobic respiration. So we remove these off. So we'll talk about the aerobic respiration. Well, this is very hard to remove. Okay. Okay, we have to change one. Now use this one. So we talk about aerobic respiration. So overview, what is aerobic respiration looks like? We all know the bacteria grow coming from the energy resource is carbohydrates, basically is glucose. You learned also in your genetics class, if there is a glucose and there is a lactose, which means there is a monosaccharides and there is a disaccharides, the bacteria are using monosaccharides first, then they're using disaccharides. And this has come out with a very tricky material in a genetics area called the lacto-operin. We're not going to talk about here, okay? It's too tricky. It's like a maze. So we be very simple. Glucose is an energy resource. Glucose going through a very simple process, which is a branch reaction, will generate a product called a pyruvate. And the pyruvate will going through a transition step called acetyl-CoA, coenzyme A, going through this circle. What is this circle called? Citric acid circle, tricarboxyl circle, or Krebs circle. All kinds of names for that. This will generate enough ATP for most of the bacteria to survive in the environments. So we want to talk about that, what it is looks like. Okay, so first thing first, we talk about here. This is called glycolysis. So what are they? We not go over structure, but we're going to go over those names. Okay. First thing, let's draw a little bit here, then we can talk. Glucose will become glucose 6-phosphates. Once you become glucose 6-phosphates, where that phosphate comes from? Comes from energy, ATP. So ATP becomes ADP. Release phosphate goes here. Glucose 6-phosphate will become fructose 6-phosphates. This is isomerization, basically. What means isomerization? The chemical components are the same, the structure is different. Fructose 6-phosphates go down, become fructose 1,6-biphosphate. This is right here. 1,6-biphosphate. Originally, there is only one phosphate. How come you have a fructose 1,6-biphosphate? Another ATP used We talk about ATP is energy currency. It's like tickets, go to see a movie or go to see a football game. They have to pay. Okay, then become fructose 6-phosphates. Fructose, I tell you one thing, it's a very organized structure. Somehow like this. Somehow like that. Very organized structure. So, they could cut down at the middle. When they cut down at the middle, they will become a chain. Glyceraldehyde 3-phosphate. That's the first thing. What you see is right here. Glyceraldehyde 3-phosphates. Okay? Then what will happen? 1,3-biphosphoglycerate. Then we go down 3-phosphoglycerate. Then go down 2-phosphoglycerate. What else we have? Phosphoenolpyruvate. The last one, pyruvate. And this is a branch, so this is the same. Now what we care about? Energy. This area, we use the ATP, so we call it the investment. Like you buy a stock, you have to pay something. Then you get benefits. You invest $100, maybe you get $1,000 tomorrow. Maybe it becomes $0 the other day, okay? That's called investment. And this is called the beneficial phase. Then what we see, we're going to see where that happens, the ATP going to be generated. Okay? 1,3-biphosphoglycerate. This is the process is very tricky. What's tricky when you look at here? There is no ATP generated. However, there's something happened, which is NAD reduced to NADH2. This is a very tricky stuff there. It's a key stuff. 1,3-biphosphoglycerate becomes 3-phosphoglycerate. Where that phosphate goes? Donate to ATP becomes, donate to ADP becomes ATP. 3-phosphoglycerate becomes 2-phosphoglycerate, basically is moved the position. 2-phosphoglycerate becomes phosphoenolpyruvates. What happened? Enolization. Enolization, what this means? Lose water, usually. Okay, usually the water lose, that's called enolization. But the last step, phosphoenolpyruvate become pyruvate. So is where this phosphate go? ADP become, with ATP becomes ATP. So, glycolysis, how many ATP generated? This is -2 ATPs. Here is 2 ATPs generated. Multiple by 2 is 4 ATPs. So you add up them together, -2 add 4 equals 2 ATPs. This is a match what we just talked about the fermentation. Fermentation is only 2 ATP generated. Is that right? That's what that makes sense. Okay, what's the difference? What's the tricky stuff? We talk about aerobic respiration. Okay, this guy will be happy. What means aerobic respiration? Which means we're going to use oxygen. And oxygen correlated with electron transfer. So, transport chain, we're going to talk about that. What's the electron transport chain? We just draw briefly one. NAD goes to NAD, goes to NADH, goes to FAD, goes to FMN, goes to FES. This is usually a couple. Okay, COQ, then go to cytochroma C, then go to cytochroma A, then go to A3, and finally goes to oxygen. This is the electron transport chain. During this process, what happened? Not only they transfer electron, they're transferring electron. So always remember, something transferring electron, something going to go out. What are going to go out? Proton going to go out. Once a proton goes out, they accumulated outside of the cell membrane system, become a potential energy. And once they accumulate more and more, they're going to come back. Okay, once this guy comes back, what happens? They will activate ATPase, which is an enzyme generated ATP. So ADP will, with phosphates, becomes ATP. Will generate. At the same time, for the bacteria, you have to do something. You're causing the movements, and the real movement is flagellar rotation. So they coupled with flagellar rotation. This theory is very important. It's proposed by a great British scientist, Peter Mitchell, in 1932, and win the Nobel Prize in 1960s. This is called chemosmosis. This is one of the ways to explain oxidative phosphorylation. So, how many ATP generate here? I do it easy, 3 ATPs. In your biochemistry class, you talk about 2.5 because you talk about phosphate, oxygen phosphate ratio. I just do 3. It's easy. So, if glycolysis is part of the aerobic respiration, how many ATP generate? You need to add 3 ATPs multiplied by 2 equals 6 ATPs. So you have 2, you need to add here 8 ATPs. Clear? That was a little bit tricky thing there. Why? In your textbook, even you learn about chemistry, biology 101, they always tell you, oh, glycolysis generates 2 ATPs. What this means? That means it's coupled with fermentation, which means without oxygen. Or we say that very frankly, is with limited amount of the oxygen. No places is absolutely no oxygen. However, if it's coupled with aerobic respiration, this guy going through electron transport chain. So the total here is 8 ATPs. Now, let's move on to the next one. We have a pyruvate. Okay, what are we going to do, pyruvate? Pyruvate going through a transition step become acetyl-CoA. Then we go through this cycle. Acetyl-CoA, first of all, becomes citric acid. Citric acid to isomerization called isocitric acid. Now, some people will say you are wrong, you're missing something there. We'll talk about bacteria. So, ascorbic acids, we're going to just skip it, okay? Isocitric acid, go here. We have alpha-ketoglutarate. Then what we go here? Succinyl-CoA. Then what we have? Succinate. Then go here, what we have? Fumarate. Then what we have? Malate. Then go here, oxaloacetate. Then you go back. This is a circle called TCA cycle. And the picture which you can show is right here. Okay? Now, it's not about chemistry class. I don't care about structure. I care about what happened for the energy. What happens for the ATP. So let's see it. The slides is there. If you're not familiar with this, it's right there. Okay, what happened? Pyruvate to become acetyl-CoA, they happened NAD reduced to NADH2. Isocitric acid become alpha-ketoglutarate coupled with NAD reduced to NADH2. Alpha-ketoglutarate becomes succinyl-CoA, happens NAD becomes NADH2. Succinyl becomes fumarate, there is FAD. Following adenine dinucleotides become FADH2. And the last one, malate, goes to oxaloacetate. There is also NAD reduced to NADH2. So we can check what it is. Yes, that's correct. What we are missing? Right at the bottom. There's when GDP becomes GTP. That's guanine triphosphates. Okay. Now how many ATP generate? That we already said. I set up you easy rule. NAD reduced to NADH2 is 3 ATPs generated. You talk about 2.5 in your biochemistry class because we talk about the oxygen phosphate ratio. And FAD reduced to FADH2, there is 2 ATP generated. And you talk about 1.5 ATPs, and we just use this one. Okay, it's easy. So how many ATPs there? This is 3 on the top. That's easy to understand. 3 right here, 3 right here, 1 right here, 2 right here, and 3 right here. So how many? 3 multiplied by 4, add 2, add 1 equals what? This is 12. Is 15 ATPs. But do not forget, glycolysis is 2 chains. It's a branch reaction. So you have the pyruvate right here, another pyruvate right here. But they both go TCA cycle. So how many there total? 15 ATPs multiplied by 2 equals 30 ATPs. 30 ATPs is generated going through a complete TCA cycle, including the top we call transition step. Okay, so here is 8 ATPs. Here is 30 ATPs. Here including this guy. So how many ATPs going through aerobic respiration? 38 ATPs. Keep in mind, this is in bacteria. How many in fungi? Eastern mode, 36 ATPs. Why? Where this comes from, the 2 ATPs? Passing the barrier of mitochondria. Because bacteria doing metabolic process is in the cell membrane system. For fungi, There you can't use. They need to do a specific cell machinery. Where are they? Mitochondria. And you pass in the barrier of the mitochondria, you have to pay the tickets. It's like you go to see the football. You have to go through the gates to pay the tickets. It does not matter how much it is. Here is $2. It's 2 ATPs. So that's why the fungi is 36 ATPs. Okay, now in your biochemistry class, you talk about 2.5, 1.5, and you can do another calculation. It's the same thing. So in order to help you, we actually on here, I have a slides which is using a new calculation, is right there. This is what we did using 2.5 and 1.5. And this is the older one we talk about is using 1.5. Oh, sorry, we're using 2 and 3. It's up to you which one to be using, but the calculation what you do is has to be uniform. Is only one set of the rules, is not mixed with different part. Okay, so what we are missing here? We talk about glycolysis. We talk about TCA cycle. We talk about the ATP generate. We talk about the electron transport chain. We talk about chemosmosis. What we are missing? How these ATP generate? Did you ever think about how this is ATP generate? They don't have the electron transport chain. Then why the ATP is still generated? This is, we have another thing we want to talk. You have to remove some. This is called substrate level phosphorylation. So we have to move this part. This is called substrate level phosphorylation. Now, obviously, substrate level phosphorylation, it is not involved in electron transport chain. But why you can do that? This comes back to delta G equals delta H minus T delta S. And delta S, sorry. Delta S minus delta H. It's entropy, and the rate to the time, the temperature. It's a thermodynamic. If delta G less than 0, spontaneous reaction will happen. If delta G more than 0, it's not happen. Need ATP to trigger. Become ADP and phosphates. And you need to keep in mind, lots of the chemical, they have ATP transfer potential and energy. And we can do is a calculation. ATP from ADP and the phosphates, there is a potential phosphate transfer power. The power kind of looks like is 30.5. And when you see 1,3-biphosphoglycerate becomes 3-phosphoglycerate. Biphosphoglycerate become 3-phosphoglycerate. What's the transfer power of phosphates? It's about 45 to 55. And the phosphoenolpyruvate become pyruvate. Phosphoenolpyruvate become pyruvate. What's the potential energy transfer power? It's about 67. Both of these are more than the phosphate transfer power of ATP itself. What this means, they could trigger this reaction, go from right side to the left side, so the ATP will generate. That's why these places could happen is ATP generation even without electron transport chain, because they have those powerful phosphate transfer chemical. So they have a stronger phosphor transfer power than ATP itself. That's why we can do substrate level phosphorylation. Now you're gonna have a question for me. There is a lot of chemical here. Glucose 6-phosphate, fructose 6-phosphates, and the fructose 1,6-biphosphates. Now, why these things doesn't happen, the ATP generate? These chemicals, they also have a phosphor transfer power. For example, let's see that glucose 6-phosphates. Glucose 6-phosphates also have phosphate transfer power. This is only around 13. Fructose 1,6-biphosphate. They also have a phosphate transfer power. This is only about 25 to 27. That's not enough. You're not going to compete with that. So the reaction cannot go the other side, cannot generate ATP. So that's substrate level phosphorylation. It's a very magical way to do. You have to have that one. If you don't have that one, lots of the anaerobic bacteria cannot survive during the fermentation. Remember, only 2 ATPs generate. Where that 2 ATPs come from, substrate level phosphorylation. You have to do with that. Okay, so this gives you a very important conclusion. Fermentation has only 2 ATPs generated through substrate level phosphorylation. This is basically, you can understand, coupled with glycolysis without oxygen. This is a key. Otherwise, it's called aerobic respiration. So, this is, we kind of explain to you the principles behind these. Most of the time, we had E. coli, Salmonella, Listeria, all those things we talk about, those major foodborne pathogens. They can do glycolysis, they can do TCA cycle, and they generate enough energy to be used. And they could also survive in the anaerobic environment. That's why we call it a facultative pathogen. Is that right? Without oxygen, with oxygen they can grow. That's the reason you do vacuum package the hot dog, still have this stereomonocytogen is going to grow. Otherwise, vacuum package could solve all the problem. So that's why it's called a facultative pathogen. But in our environment, there are some of the bacteria, listed right here, is we call anaerobic respiration. What's the difference? We mentioned earlier. Their end electron acceptor is not oxygen, is those other things. Could be nitrogen, could be carbon dioxide, could be ferric acids, could be fumarate even, they could be sulfide. And you see these names, it's understandable. For example, disulfur vibro, what means disulfur vibro? Vibro? Vibro means a shape. It's curved, a little bit of circle, a little bit of curved. What's a disulfur? So you reduce sulfuric acids become hydrogen sulfide. So instead of you have a water, you have H2S. And look at the messages. It's carbon dioxide is an electron acceptor, and finally they generate a message. So all in all, you can see these things. Okay, how many ATPs they're going to generate? It's very magic. It's variable. Their ATP is between 2 and 36. We don't know. Because 2 is a minimal for anaerobic respiration. 38 is for aerobic respiration. Their anaerobic respiration, lots of them are between that. And for them, they also had glycolysis. They also had electron transport chain, but some of them will be modified. Some of them even have a reversal electron transport chain. The reason why it's a little bit different, because most of these are environmental microbiology. They come from different resources. It could be from Yellowstone National Park, could come from Great Salt Lake City Lake, could have come from Antarctic area, and those need to be survived in a very specific environments. And they have to use other than oxygen as their energy resource, which means the electron acceptor. Otherwise, they cannot survive. Okay, so we are simply just telling you, this is a last slide to talk about that. Very important is this table. This table will tell you how many they're going to generate. By all means says, this could be using in your exam. We're going to talk about the energy generated. So we're going to go over this table. This is, you can mark 3 star. This means it's going to be used in the exam for questions. So let's talk about that. Okay, look at these rows. Metabolic process, we mentioned aerobic respiration on the top, anaerobic respiration, and then fermentation. Second column is what are the pathways used. And we mentioned about that. Aerobic respiration, we have glycolysis, we just mentioned, and we have a TCA cycle. TCA cycle is an acronym of tricarboxy acid gas. Tricarboxy acid cycle. Fermentation, only glycolysis, and they couple. And very interesting, the next question. Terminal electron acceptor. That means the final electron acceptor. Aerobic respiration is oxygen. Anaerobic respiration is other inorganic chemical, not oxygen. So that could be nitrate, nitrite sulfate. Fermentation, organic molecular. Here, I want to explain another thing to you. When you see pyruvate become lactic acid, this NADH oxidized become NAD. Here, we give another name called this is lactic acids, but we also say this is derivatives of pyruvate. So we still say quotation mark, this is pyruvate. So that's why this is also organic chemicals. Okay? That's the reason. That's why it says pyruvate or derivatives. The derivatives referred here is lactic acid. ATP generates with substrate level phosphorylation. Aerobic respiration, how many they have? 2. Going through glycolysis. 2 in the TCA cycle. Where are they? Right here. This is 1, and then we have 2 cycles, so 2 ATPs. Substrate level phosphorylation. So total is 4. Anaerobic respiration, I didn't draw here, but they tell you it's also 4. Their glycolysis is a little bit modified, and their TCA cycle is a little bit modified. I want to also mention about something. This is in the microbiology textbook, but I don't want to go too detailed. What we talk about here, this is a very standard glycolysis. In other words, we have another name for that. It's called Eboden-Meyerhof pathway. Is that right? And you should know that if the soil microbiology, they will have a modified glycolysis. We call it Eboden-Doulhoff pathway. It's different. Basically, this investment stage is the same, but this beneficial phase is a little bit different. So just want to let you know, it's not the same thing, but very similar. So we don't go detail about that, because those usually the microbiology major, not even at WVU, let's say in University of Pittsburgh, if you're a microbiology major, they will teach details about that part. Okay, so just want to let you know, anaerobic respiration, 2 ATPs, we modify the glycolysis, I could say, or 2 ATPs, we modify the TCA cycle. Fermentation, how many generate? Obviously, only 2 ATPs from glycolysis. ATP generates 3 oxidative phosphorylation. Let's talk about the fermentation. Very simple. Because there's no oxygen, so no ATP going through oxidative phosphorylation. But the tricky thing is that, how many go through aerobic respiration? Through oxidative phosphorylation. That's tricky. How many here? 3 right here. So, 3 multiplied by 2 equals 6. Okay, how many here are oxidative phosphorylation? You need to take out this one down. So what this means? 30 minus 1 equals 28. This 28 add up here equals 34. That's what the 34 comes. Okay? So that's why so right here is 34 from aerobic respiration. Anaerobic respiration here is very briefly because different bacteria going through modified TCA cycle, it's different. So we're not going to talk about every single thing. Usually we have another class. Before in plant science division, you guys should offer soil microbiology, water microbiology. They will talk about each individual. Each individual could be teach about 3 weeks, about a month, to talk about every single thing. But right now we don't have those classes, so this is just omit to just talk very simple. So that's 32. Like I said, it's between 2 and 34. So, finally, total ATP generated. Aerobic respiration 38. Anaerobic respiration somehow between 2 and 38, 36 or less. They gave you an exact number. So we could say anaerobic respiration is less than 36 ATPs, but more than 2. Let's say the X, somewhere between that. Okay? Anaerobic respiration, which means fermentation, is only 2 ATPs. Okay, so this is basically what I have in these slides. Now let's go over these slides again. This is one. We basically talk about aerobic respiration, anaerobic fermentation. Now, all of these normal bacteria we talk about in this class so far, they belong to chemoheterotrophs. It is different from the algae in the river or in the lake. They use light as an energy resource. That's a different name. And I skip that part because that will be a very tedious table to explain everything. Because chemo is one part, hetero is one part, and the troph is another part. That means a 3 section. So how many different combinations? At least 9. Okay, so that's the first thing. Second, this is I already talked about at the beginning from energy transfer standpoints, talk about aerobic respiration, anaerobic respiration, and ATP. This one, is also very similar to what we talk about, but we emphasize you is electron transport chain coupled with proton motive force, and we mentioned substrate level phosphorylation. This is the formula for fermentation. Homo, and hetero. This means fermentation in a conclusion slide tells you ATP through substrate level phosphorylation coupled with glycolysis right there. Apply the results from fermentation. Aerobic respiration, glycolysis, TCA, electron transport chain. Then this described the Ebden-Meyerhof pathway. Look at the top, Ebden-Meyerhof pathway. That's usually the normal glycolysis what we talk about. Glycolysis we mentioned. Summary of glycolysis. Oxidative phosphorylation, this is electron transport chain. I draw there just briefly. Electron transport chain, furthermore, chemosmosis, what it talks about. Basically, electron transfer coupled with proton repel out. Generate potential energy, proton motive force. Then, too many outside, they have to come down. Activate ATP synthesizer, then ATP will be synthesized. Coupled with active transport part with bacterial rotation. Bacterial flagella rotation. This is how they generate the energy. Then we move on to transition step of TCA cycle. This is a TCA cycle. How we talk about that? This is a calculation using a new rules. This is a calculation using old rules. I would say you can keep this one because this is easy to do 2, 3 compared to 2.5 and 2.5 and 1.5. Anaerobic respiration, and the final, very important, is the conclusion table. Okay, so this end up with we have a briefly introduction to you all the biochemistry reaction. In order to help you, exam 3, we also gonna give you some practice exam questions and we explain it. Otherwise, it's too complicated. When you open these notes, you may not find it. So it's the same thing. We will give you 10 questions, 15 we'll explain what the answer. Okay, let you prepare for the exam. Okay, so that's all we have.